Hello, and welcome to the Quantum Slumber. Tonight, we're going to follow a strange idea, one that sounds like a myth the first time you hear it, and then refuses to go away no matter how carefully you try to explain it away. Imagine two particles born together in the same quiet, violent moment, a flash inside a laboratory, or a faint event deep in the early universe. They drift apart, farther than any hand could reach, farther than any voice could travel. And yet, when you finally measure one of them, its polarization, its spin, the direction it chooses to be, the other one answers with a matching response, as if the universe wrote them into the same sentence. Einstein called it spooky action at a distance, not because he wanted it to be spooky, but because it threatened something sacred. The idea that distance separates, that causes stay near their effects. That reality is made of independent pieces, each carrying its own private truth. And here's the unsettling part. Entanglement isn't a rumor from the fringes of science. It's one of the most tested, most repeated, most stubbornly verified features of the quantum world. Again and again, in different labs, with different systems, across longer and longer distances, the same eerie pattern returns. So tonight, we're not asking whether the story is strange. We're asking something simpler and deeper. What kind of universe allows it at all? As we go, we'll keep the pace gentle. No heavy math, no racing, just a calm walk through the ideas, letting each one settle before we take the next step. Because the goal here isn't to overwhelm you. It's to make the impossible feel quietly understandable. And if you enjoy these slow, bedtime journeys into the deeper edges of science, you're warmly invited to like the video, subscribe, and share a thought in the comments, maybe where you're listening from tonight, or what first made entanglement feel real to you. It helps this little channel find more curious minds who want to rest and wonder at the same time. Now, take a slow breath. And before we call this thing magic, let's make sure we're not expecting the wrong kind of connection. Before we go any farther, it helps to clear away a few myths that cling to entanglement like fog on a cold window. The most common one is the movie version. Two particles talking to each other instantly across space, sending messages faster than light. That image is dramatic, but it isn't what the experiments show, and it isn't what the mathematics allows. Here's the calm truth. Entanglement does not give you a faster than light mailbox. If you measure one particle from an entangled pair, you don't get to choose the outcome. You don't get to tap out a code. You don't get to decide spin up means yes, spin down means no. The result that appears in your detector is stubbornly random. It's like reaching into a bag and pulling out a marble without looking. No matter how badly you want red, sometimes you get blue. Quantum mechanics will not let you steer that moment. And that one fact, the randomness of each individual result, is the key that quietly locks the door on faster-than-light communication. Because communication requires control, it requires intention. If I can't choose what I send, then I'm not sending anything at all. I'm just observing. So, what is happening when people say the other particle responds instantly? What's happening is correlation, a pattern that only becomes visible when you compare outcomes from both sides. A gentle way to picture it is this. Imagine two sealed envelopes prepared together. Each envelope contains a slip of paper that will match the other in a specific way. Maybe they'll always add up to the same number, or they'll always be opposites. Now you take one envelope to one side of the world, and someone takes the other to the other side. When you open yours, you learn something about what the other person will find. Not because your envelope sent a signal across the planet, but because both envelopes were prepared as one coordinated system from the start. Entanglement is like that, except stranger. In the quantum case, it isn't that the answer was written down and hidden inside each envelope in advance. The quantum description says the pair shares one combined state, and the specific outcomes don't settle into place until measurement happens. But even then, on your side, you still see randomness. Your data looks like noise. The meaning is hidden. The pattern only shows itself later, when the two observers bring their notes together and compare them through ordinary, slower-than-light channels, a phone call, a fiber optic cable, a radio signal, whatever you like. Entanglement gives you a shared structure in the results, not a shortcut for sending them. This is why physicists often say, entanglement is instant, but it doesn't carry usable information by itself. It's an eerie agreement, not a message. And once you see that difference, correlation versus communication, the fear that causality is being smashed to pieces starts to soften. The universe isn't letting you whisper secrets across galaxies. It's showing you something more subtle, that two distant measurements can be linked by a single underlying quantum description. To really feel how that can be true, we need one gentle step into what a quantum state actually is. To make sense of entanglement, we need a soft, steady footing. 3 ideas that sound intimidating in the textbooks, but feel surprisingly natural when you slow them down: state, superposition, and measurement. In the everyday world, an object seems to carry its properties like luggage. A coffee mug is on the table, or it isn't. A coin is heads or tails. A light switch is up or down. We don't usually worry that reality might be undecided. We assume the world is made of little facts that exist whether we look at them or not. Quantum physics asks us to hold a different picture, gently, without forcing it to match our instincts too quickly. Start with the simplest word: state. A state is not a thing you can touch. It's more like a complete description of what a system is capable of doing next. In classical life, that description can be very direct. If I tell you a ball's position and speed, you can predict where it will roll a moment later. The state is a neat list of properties. In quantum physics, the list exists too, but it doesn't behave like a list of fixed answers. It behaves like a description of possibilities, with weights and phases, like a kind of structured probability. And that structure matters. It's not just ignorance. It's not, we don't know yet. It's closer to, the system isn't committed to a single classical story. This is where superposition enters, one of the most misunderstood words in all of science. People hear superposition and imagine a particle being literally in 2 places at once in the way a character can be in 2 scenes at once in a movie. But the calmer, more accurate picture is that the quantum state contains multiple possible outcomes at the same time, in a way that allows them to interfere, to reinforce or cancel each other, like overlapping ripples in water. Think of it like music instead of objects. A guitar string doesn't choose one point in its vibration. It holds a pattern, peaks and troughs, spread along the string. When you hear the note, you're hearing the whole pattern. A quantum state is like that. A pattern of potential outcomes spread across what can happen. Now, here's the crucial shift. Superposition is not the same thing as uncertainty. Uncertainty, in ordinary life, is about our lack of information. If you flip a coin and cover it, you might be uncertain whether it's heads or tails, but the coin is already one or the other. Your ignorance doesn't change the coin. A quantum superposition is different. It's not simply hidden heads or hidden tails. It's a state where the physics keeps multiple outcomes in play, in a way that creates interference patterns that cannot be explained by any story where the result was decided all along. That's why, when you run a double-slit experiment with single particles, you don't just see 2 tidy piles building up behind the slits. You see a delicate pattern of bright and dark bands, an interference pattern appearing one particle at a time, as if each particle traveled through a field of possibilities, not just one path. So, the state is a structured set of possibilities. Superposition is the fact that multiple possibilities can coexist in that structure, in a way that leaves fingerprints in the statistics. And then comes the word that causes so much discomfort: measurement. In everyday language, measurement sounds passive, like shining a flashlight on something that's already there, like reading a number from a gauge, like checking the weather. But in quantum physics, measurement is not just reading. It is an interaction, a physical event, where the system becomes tied to an outcome that can be recorded, repeated, and shared. A useful way to think of measurement is as the moment the quantum state stops being private math and becomes public fact. Before that moment, the state can carry many possibilities. After that moment, the world contains a definite result. A detector clicked here, not there. A polarization was recorded as this, not that. The spin was found up along a chosen axis. This is where people often say, the wave function collapses. That phrase can sound violent or mystical, but you can treat it as a practical label. The theory updates from a spread of possibilities to a single outcome because the system has interacted with something large enough, an apparatus, an environment, a record, that the alternatives stop interfering with each other. In other words, measurement is the point where you can no longer keep the different possibilities in phase, like overlapping ripples. The possibilities stop acting like a coherent pattern and start acting like exclusive outcomes. One story becomes real in the everyday sense. And it's important to say this clearly because it keeps the whole topic grounded. Quantum measurement does not mean a human mind creates reality by looking. A measurement happens when the system becomes correlated with the outside world in a stable way. A photodiode doesn't need consciousness to click. A Geiger counter doesn't need curiosity. The observer can be a piece of hardware, a stray atom, a warm room, anything that forces a durable record. So, why do we talk about observation at all? Because what matters is not the eyeballs. What matters is the moment information about the system becomes available in a way that can, in principle, be checked by more than one thing. Measurement is when the system becomes part of a larger web of cause and effect. Now, with state, superposition, and measurement in your hands, you can see why entanglement is not just two particles communicating. It's not a secret wire. It's what happens when the state itself refuses to split neatly into two independent descriptions. Because quantum states can describe not only individual objects, but whole systems. Sometimes the most honest description of two particles is not, particle A has its state, particle B has its state. Sometimes the most honest description is a single shared state for both together. A combined pattern of possibilities for the pair as a unit. And when that happens, measurement on one side doesn't send a message. It simply reveals one face of a shared structure, like touching one corner of a stretched fabric and seeing the whole sheet respond in the pattern it already had. That is the quiet foundation beneath the strangeness. Quantum physics describes reality not as a catalog of isolated properties, but as states, patterns of possibility, that can belong to single things, or to pairs, or to entire networks. And once you accept that a system can be described as one connected state, the next idea becomes almost inevitable. Two particles can share not two separate stories, but one. Imagine you're holding two coins in your hands, one in each palm. In the everyday world, each coin has its own quiet truth. Even if you refuse to look, each coin is already showing heads or tails. Two separate objects, two separate stories, two answers, waiting. Quantum entanglement is the moment that simple picture stops being the most honest one. Because sometimes, in the quantum world, the best description of two particles is not, this one has its state, and that one has its state. Sometimes the cleanest, truest description is a single shared state that belongs to both at once. One combined wave function that refuses to split into two independent pieces. That phrase, one shared wave function, can sound abstract. So, let's make it gentle. A wave function is not a physical wave sloshing through space like water. It's a mathematical description of possibilities. What could happen if you were to measure a system and how those possibilities relate to each other? For one particle, it's already a little strange. For two particles together, it becomes a new kind of creature, because the wave function can describe the pair as a whole, including relationships between them that are stronger than anything classical intuition expects. Here's the simplest way to feel it. With entanglement, the pair has a rule, an internal agreement, that reality must obey when you finally check. Not a rule like a message being sent, but a rule like a pattern that was there from the start. A classic example uses spin, which you can picture as a tiny built-in orientation, a quantum yes-no property you can measure along a chosen direction. Don't worry about imagining it as a literal spinning ball. It's more like a label nature hands you when you ask the particle a specific question. Now suppose two particles are created together in a way that locks their spins into a relationship. One common relationship is, if you measure them along the same direction, you will always find opposite results. If one comes out up, the other will come out down. In a normal classical mindset, you might assume that means each particle secretly carried its answer the whole time, like two envelopes prepared in advance. One says UP, the other says down. You open yours and discover what was already written. But entanglement is subtler than that envelope story, because in a fully entangled state, the pair is not best described as particle A is secretly up and particle B is secretly down. Instead, the pair is described as a superposition of two joint possibilities at once. A is up and B is down. A is down and B is up. Those aren't two separate guesses about what might be happening. They are two branches of a single combined description. A shared wave function that says the pair will be opposite, but no single particle owns an answer by itself. And that last line is the heart of it. In entanglement, the certainty lives in the relationship, not in the individual objects. It's as if the universe is saying, I will guarantee the pattern, but I will not assign private properties to each particle ahead of time. This is why entanglement is often described as non-separability. The system does not break into two independent parts with their own complete descriptions. The whole carries information that the parts do not contain by themselves. If that sounds philosophical, here's a more grounded way to say it. A shared wave function means the probability map is written for the pair together. It doesn't only tell you A might be this and B might be that. It tells you A and B together might be this joint outcome, and A and B together might be that joint outcome, with no way to rewrite it as two separate independent maps without losing something essential. And when you measure one particle, you're not pushing the other one around. You are simply taking that shared map and forcing it to commit to one of its consistent joint outcomes. So if you measure particle A and find up, the shared wave function updates to the branch where particle B is down, along the same measurement direction. Not because particle A sent a command across space, not because anything traveled faster than light, but because the pair was never two fully separate stories to begin with. It was one story with two locations. This is where the word instant sneaks in and causes trouble. The correlations can appear instantly in the sense that once you compare notes later, the pattern is perfect. No delay, no gradual matching, no partial agreement. The relationship holds with a kind of eerie confidence. But that does not mean a usable signal moved from A to B at the moment of measurement. You can't control the outcome you get on A. You can't choose up like pressing a button. You only receive a random result, and the randomness is exactly what prevents entanglement from becoming a faster-than-light telephone. Entanglement gives you a bond, not a broadcast. A helpful metaphor, soft but useful, is to imagine two pages of the same book, far apart. You open one page and see a sentence. That doesn't cause the sentence on the other page to be what it is. It reveals that both pages belong to one consistent story. The connection is logical, not mechanical. Of course, entanglement is more profound than a printed book, because the story is not fixed in advance in the classical way. But the point holds. Correlation does not require communication. Another way to feel it is this. Classical physics encourages you to think the world is made of things with properties. Quantum entanglement suggests the world may also be made of relationships that are just as real as the things themselves. The particles are real, the clicks in detectors are real, but the deepest fact may not be particle A had spin up all along. The deepest fact may be the pair has a shared structure that will always produce matching outcomes when questioned in the right way. And that shared structure is the wave function. It is not a ghostly mist. It is a precise object in the mathematics, so precise that it predicts the exact statistical patterns we see in experiments. It tells us what outcomes can happen and how strongly they're linked. It predicts when correlations will be weak, when they'll be perfect, and when they'll do something that no classical hidden answers story can reproduce. If you let that settle for a moment, entanglement begins to feel less like magic and more like a new rulebook. Not spooky influence, but shared description. Not one particle controls the other, but the pair is one system, even when space separates them. And this is the quiet promise of the topic. The strange connection is not a loophole in physics. It's physics being consistent in a way our everyday instincts never had to learn. In just a moment, we'll meet the reason this idea bothered Einstein so deeply. Because if the universe truly works this way, it forces us to ask what we mean by reality when nobody is looking. In 1935, three physicists, Albert Einstein, Boris Podolsky, and Nathan Rosen, sat with a discomfort that wouldn't go away. Not the kind of discomfort you can solve with a new calculation or a cleaner experiment. This one was quieter and deeper. They looked at what we've just described, two particles prepared together, then separated, still behaving like one shared system. And they asked a simple question, almost childlike in its fairness. If these particles are far apart, what exactly is real about each one? Their paper is remembered by the initials EPR, and it isn't a rant against quantum mechanics. It's more like a formal letter to reality written in careful language, trying to protect a certain kind of common sense, without resorting to superstition. EPR began by setting a standard, a rule for when we're allowed to say something is real. They proposed what's often called a criterion of reality. If you can predict the value of a physical quantity with certainty without disturbing the system, then there should be something real in the world corresponding to that quantity. That's a mouthful, but the instinct behind it is familiar. If you can know something for sure about an object without touching it, without nudging it, heating it, poking it, then maybe that something was there all along. Now they bring in the entangled pair. Imagine two particles created together in a way that links them. Not linked by a wire, not linked by a signal, but linked by a shared quantum state. Then they drift far apart, so far that whatever you do to one cannot physically affect the other quickly enough, if relativity is right and signals are limited by the speed of light. Here's the unsettling move. You measure particle A, and instantly in your notebook, you can predict what you would find if you measure particle B in the same way. Not approximately, not statistically, with certainty. So EPR says if that prediction is certain and if particle B is far away, then your measurement on A shouldn't be able to reach out and change the physical condition of B. Because if it could, then either information traveled faster than light, or the universe allows distant objects to be directly influenced in a way that makes separation meaningless. Einstein did not like that idea. He wanted a universe where distance meant something. So EPR leans on locality, the belief that what you do here cannot instantly rearrange reality there. Under that assumption, they argue something striking. Particle B must already have had the property you're now able to predict, not necessarily as a neat, visible label, but as something real in the world, an element of reality, a hidden fact, a value that exists whether you measure it or not. And if that's true, then quantum mechanics, at least in its standard form, doesn't tell the whole story, because the wave function by itself doesn't assign those definite values in advance. It assigns probabilities. So EPR's conclusion is not quantum mechanics is wrong. Their conclusion is more precise, and in a way, more daring. Quantum mechanics is incomplete. Incomplete like a map that predicts the coastline correctly, but leaves out the roads. Useful, powerful, accurate in its domain, yet missing something that a deeper theory might restore. This missing something is what people later loosely call hidden variables. EPR didn't provide a complete hidden variable theory in the modern sense. They didn't hand you an equation that replaces the wave function and predicts every result. Instead, they made a logical opening. If the world really obeys locality, and if the world really has definite properties independent of observation, then there may be additional variables, information not captured by the wave function, that determine the outcomes. They were trying to rescue a certain picture of reality. Objects have properties. Properties exist before we look. Space is meaningful. Influence needs time to travel. In that picture, entanglement would be strange, but not mystical. The two particles could still be correlated because they were prepared together, like two dancers learning the same choreography before stepping onto separate stages. Once separated, they aren't sending signals. They're simply revealing a shared plan written at the beginning. That at least is the hope. But EPR also knew where their argument bites hardest. Because quantum mechanics doesn't just say, we don't know the value until we measure. In many cases, it says something even sharper. The value is not defined in the usual sense until the measurement context exists, and EPR found that unbearable. If quantum mechanics is complete, then it seems to imply one of two uncomfortable things. Either measurement on A somehow changes what is real about B, despite the distance, or reality itself is not made of definite properties, but of potentialities that only become definite in the act of measurement. EPR wanted neither. So they drew a line in the sand. A complete physical theory, they argued, should account for those elements of reality that must exist if locality is true and predictions can be certain. And in that moment, the debate stopped being a vague discomfort and became a structured problem. A problem you could argue about with logic instead of mood. It's also worth noticing the emotional tone underneath EPR, because it's very human. Einstein wasn't afraid of weirdness. He helped invent it. He was afraid of a universe that seems to deny separateness, where two far-flung places are not truly independent in the way our instincts insist they should be. The EPR paper is an attempt to keep the cosmos calm and reasonable, to say, there is a deeper layer we haven't seen yet, a layer where the strange correlations have an explanation that doesn't require distance to collapse. And for a while, that idea felt plausible, almost inevitable. Because physics has a history of doing this, discovering that today's mystery is tomorrow's missing variable. Heat becomes molecular motion. Magnetism becomes moving charge. The sky's wandering lights become gravity's clockwork. So why not this? Why not entanglement as a signpost pointing toward a deeper, hidden structure? And yet, even as EPR made their case, another possibility was quietly forming on the other side of the room. Maybe the world isn't obligated to match our preferred definition of reality. Maybe the wave function isn't a temporary placeholder while we wait for hidden variables. Maybe the unsettling feature is the feature. And that's where Niels Bohr enters, calm, stubborn, and almost poetic in his insistence that measurement and description are not accidents at the edge of physics, but part of what physics is. Niels Bohr didn't answer the discomfort with a new hidden mechanism. He answered it by changing the rules of what counts as an answer, quietly, almost politely, like a door closing without a slam. Bohr didn't counter EPR with a secret machinery tucked behind the wave function. He countered it by questioning the demand itself, the demand that reality has to come packaged the way classical intuition wants it. Bohr's view, in his own careful language, was that a measurement is not a passive peek at a pre-written script. The measurement is part of the story. The way you choose to ask the question, what you measure, how you measure it, what counts as the apparatus, is inseparable from what it even means to say the system has a property. This wasn't Bohr being evasive. It was his version of honesty. He leaned on a principle he'd been shaping for years: complementarity. Certain descriptions of a system, like wave-like and particle-like, or different components of spin, are not wrong. But they can't be fully applied at the same time. They are mutually exclusive ways of making sense of what the system can show you, depending on the experimental arrangement. So, when EPR says we can predict the far particle's value without disturbing it, Bohr hears something different. He hears, we have chosen an experimental context that defines what counts as a value. And to Bohr, that context is not a small detail. It's the whole point. In other words, Bohr's discomfort wasn't with entanglement being odd. His discomfort was with the assumption that no disturbance means no influence at all. Even if nothing touches the distant particle physically, the conditions for meaningful statements about it have changed because the combined system and the measurement choice belong together in the quantum description. This is where sleepy science becomes strangely calming if you let it. Because Bohr is reminding you that nature isn't obligated to match the categories your mind finds comfortable. Nature can be consistent without being familiar. It can be lawful without being intuitive. And quantum mechanics, in Bohr's hands, becomes less like a magic trick and more like a strict rule about what can be said and when. Around the same time, another brilliant mind looked at this growing strangeness and decided it needed a name. Erwin Schrödinger coined the word entanglement, Verschränkung, to describe how quantum systems can become so deeply linked that you can't write a complete description of one without referring to the other. Not two objects with matching settings, not two particles sending messages, but a single mathematical object, a shared state, stretched across what looks to us like distance. Schrödinger understood something important. Once entanglement exists, it isn't just a weird feature. It becomes the typical situation. In the real world, systems interact. They bump into each other. They exchange energy. And quantum interactions naturally create these shared states. So, Schrödinger did what great thinkers often do when they're worried people are getting too comfortable. He built a parable, a sealed box, a fragile trigger, a quantum event with a 50-50 outcome, and inside, a living cat. If the quantum event is truly left unresolved until measurement happens, then, so the story goes, the entire system becomes a superposition, alive and dead, held in the same breath. Schrödinger didn't write this to celebrate mystery. He wrote it as a warning flare. Be careful how you talk about measurement and reality, because if you push the language too literally, you end up with absurdity. The cat, in other words, was a stress test. It revealed a tension that never fully went away. Quantum theory works with extraordinary precision, yet the act of measurement sits at the border between the microscopic and the everyday. Is measurement a physical process like any other, or is it a special kind of update? Where does the quantum description stop and the classical description begin? Bohr's answer was, essentially, stop asking for a description that erases the role of the measuring arrangement. Schrödinger's cat was essentially, don't pretend that your words about superposition scale up without consequence. Between them, they shape the mood of the entire entanglement debate, not as a single puzzle, but as a pressure point, where physics, language, and intuition all press against each other. And then something surprising happened in the decades that followed. For a long time, this felt like a philosophical argument that could go on forever. Bohr insisting the questions were ill-posed, Einstein insisting reality couldn't be that dependent on observation, Schrödinger insisting the story was being told in a way that led to nonsense. But the universe had one more move, because eventually, a new kind of thinker arrived, someone who asked, if Einstein's hidden variables idea is right, should it leave a trace, a mathematical fingerprint, a limit that nature must respect? And with that question, the whole debate began to drift away from pure interpretation and towards something far more decisive: data. There's a particular kind of argument that can last forever. You can sit in a comfortable chair and debate what's really real, what counts as a cause, and whether nature must be local or deterministic or both. You can trade philosophies like cards, and for decades, that's exactly what the entanglement debate felt like. Einstein pulling one way, Bohr pulling another, and everyone else trying to decide which kind of discomfort they could live with. Then, in 1964, a quiet shift happened. John Bell looked at the whole puzzle and asked a different question, one that sounds almost too practical to belong here. If Einstein is right, what pattern should the data obey? Not a story, not an interpretation, a numerical constraint. Bell's move was so powerful because it didn't require you to pick a favorite philosophy ahead of time. It only required you to be clear about two ideas that many people carry without even noticing. The first idea is locality. What happens here shouldn't be instantly influenced by something far away. If two things are separated, then any influence should have to travel through space, and it shouldn't outrun light. The second idea is usually called realism, but in this context, it means something very specific, that measurement results reflect properties the system already had. Even if you haven't looked yet, the properties are there, waiting. Put those together and you get what people call local realism. It's the worldview behind a lot of everyday intuition. Objects have definite attributes and nothing reaches across space faster than light to change them. Now here's the subtle twist. Bell wasn't saying local realism is obviously correct. He was saying, if you insist on it, then you're making a promise about the statistics you will see when you compare measurements on two separated systems. And that promise can be written down. To feel how this works, imagine a very gentle setup. Two particles are created in a shared state and sent in opposite directions. Far apart, two experimenters, call them Alice and Bob, each choose one of a few measurement settings, like rotating a polarizer to one angle or another. They record outcomes that are simple: up or down, plus or minus, horizontal or vertical. If local realism is true, then the particles must carry something like an instruction set. Not necessarily a literal list of commands, but some internal variables, hidden variables, that predetermine how each particle will respond to each possible measurement choice. And because of locality, Alice's last-minute choice of setting can't reach across space to change Bob's outcome. So the outcomes should behave like this. The correlations between Alice and Bob's results are limited by the fact that they are built from pre-existing instructions plus local choices. This is where Bell introduced an inequality, one of several closely related forms, that functions like a fence around what local hidden variable theories can produce. If your world is local and realistic in that sense, the strength of correlations can't exceed a certain bound. You don't have to memorize the math to understand the meaning. Think of it like this. If the particles are just carrying pre-written answers, then there's only so much coordination they can display across different settings. They can match well for one angle or another, but not in a way that beats the arithmetic constraints of having fixed answers for all the possible questions at once. Bell showed that quantum mechanics predicts something stronger, correlations that break the fence. In one common version, the CHSH inequality, you form a particular combination of correlations from 4 different pairs of settings, 2 choices for Alice, 2 for Bob. Local realism says that combination can never go above 2. Quantum mechanics says it can go as high as about 2.828. That doesn't sound dramatic until you realize what it represents. It represents a universe where you cannot keep all of these comforting ideas simultaneously, that measurement outcomes simply reveal pre-existing values, and that no influence or dependence connects the distant choices. Bell's theorem doesn't tell you which idea to abandon. It tells you that keeping both leads to predictions that disagree with quantum mechanics. And then it offers something almost shocking for a topic that had been half philosophy. It offers an experimental decision, because now the entanglement debate isn't only about what words we prefer: collapse, hidden variables, context, many worlds. It becomes a question with a scoreboard. Either the correlations will obey Bell's inequality and local hidden variables survive, or the correlations will violate it, and something deep in local realism has to give. This is why people say Bell turned metaphysics into physics. It was no longer enough to argue that quantum mechanics felt incomplete. If you wanted hidden variables, you had to face a precise requirement. They couldn't be both hidden and purely local in the old classical sense. At least, not if experiments keep agreeing with quantum predictions. And notice what Bell's theorem does not say. It does not say we can send signals faster than light. The outcomes are still random in a way that keeps messaging impossible. It does not say everything is connected in the warm, mystical sense. It says something far more specific and far more unsettling. The world's correlations do not fit inside the box that local realism builds. So by the mid-1960s, the problem had changed shape. Entanglement was no longer just a strange consequence of the equations. It became a fork in the road for reality itself. Either the world is not local in the way we instinctively imagine, or it is not real in the sense of having definite values before measurement, or the story is more subtle than both. And once a question becomes testable, it doesn't stay a philosophy question for long. From that moment on, the debate started migrating, slowly, patiently, out of lecture halls and into labs, onto optics tables, into the careful craft of counting photons, switching settings, and watching whether nature respects Bell's fence, or steps right over it. In the years after Bell wrote his Inequality down on paper, entanglement had a new kind of weight. It wasn't only a strange prediction anymore. It was a promise that the universe could be questioned in a way that didn't depend on taste or philosophy, or which interpretation you happen to prefer. A promise is a delicate thing, though. You can't cash it in with a clever argument. You can only cash it in with an experiment that refuses to be fooled. And in the early days, the experiments were brave in a very ordinary way. They weren't giant machines filling football fields. They were benches, optical tables, tubes and lenses and detectors that clicked in the dark. They were the kind of setups that require patience, not because the idea is complicated, but because reality is. The goal was simple to say out loud. Create pairs of photons that leave the same source with linked polarizations. Send them to two separate measurement stations. Choose a measurement setting on each side, an angle for a polarizer, a direction to ask the photon about, and then record the outcomes. Do this again and again and again until the pattern becomes too clear to dismiss. If the world is governed by local hidden variables, if each photon carries a private instruction set and nothing travels between them faster than light, then the correlations between the results must stay under Bell's limit. If quantum mechanics is right, the correlations can climb above it. That's the whole wager, a single ceiling and a pattern that either respects it or breaks it. One of the first experiments to take that wager seriously was performed by Stuart Friedman and John Clauser in the early 1970s. Their method relied on a dependable way of producing correlated photons. An excited atom emits two photons in succession, and the physics of that emission tends to tie the photons' polarizations together. It's not that the photons are identical. It's that they're born from one event, like two notes from one chord. Then comes the hard part, catching them. You place polarizers in the paths of the photons. You rotate those polarizers through different angles. You watch for coincidences, two detector clicks that happen close enough together in time that you can reasonably treat them as a pair from the same emission. You collect statistics. You build a correlation curve. And what Friedman and Clauser found was exactly the kind of discomfort Bell predicted for any local hidden variable worldview. The correlations violated Bell's inequality. Not by a poetic interpretation, by numbers. It would be tempting to say, so that settles it. But good physics almost never settles on the first clean-looking result, because the world is full of ways to imitate truth. A measurement can be biased without anyone meaning it. A detector can miss events in a way that quietly selects only the convenient subset. A setting can be stable in time, allowing a hidden variable model to prearrange a response. The more extraordinary the claim, the more you interrogate the apparatus itself. So, the conversation immediately sharpened. It became less about whether quantum mechanics was elegant, and more about whether the experiment left any escape hatches. Two escape hatches became famous, and they mattered so much that they earned a special name, loopholes. The first was the detection loophole. Early photon experiments didn't detect every photon. In fact, they detected only a fraction. Imagine trying to learn the true shape of a coastline by photographing it through fog. You see something. You see enough to get excited. But a skeptic can always say, what if the fog is selective? What if you're only seeing the parts that make your conclusion look strong? In the language of these experiments, the worry was that the detected events might not be a fair sample of all the emitted pairs. If some hidden variable mechanism could influence which photons get detected, depending on the measurement angle, then the subset you record could mimic the quantum violation, even if the underlying world were local and predetermined. This doesn't mean the experiments were wrong. It means the experiments were not yet airtight. The second was the locality loophole. This one cuts closer to the heart of the mystery. When you test Bell's inequality, you're not just measuring outcomes, you're also choosing how to measure. On each side, you decide a polarizer angle, and that choice is supposed to be independent. The worry is that if the measurement settings are known too early, or if there's enough time for any ordinary signal to travel from one side to the other, then the two photons could coordinate through normal physics, at light speed or slower, and fake a quantum-looking correlation. So, the dream experiment would be one where, by the time the photon arrives and the setting is chosen, there simply isn't time for any message, any influence, to cross from one station to the other and help. In other words, you want the two measurement events to be separated in a way that even light can't bridge in time. That is a subtle requirement, but it's also a beautiful one. It's not asking the universe to do magic. It's asking the experimenter to remove every ordinary way for coordination to happen. As the 1970s moved forward, more tests were performed, and the results continued to point in the same direction. Violations of Bell's inequality appeared again and again. The evidence was stacking up, but the loopholes remained part of the story, like a faint draft in a room you're trying to seal. Then came Alain Aspect and his team in the early 1980s, and their experiments felt like a turning point, not because they were the final word, but because they attacked the locality concern with real creativity. Aspect's central idea was to keep the measurement settings from becoming predictable. Instead of setting the polarizer angles and leaving them fixed while photons traveled, he arranged for the effective measurement setting to be switched rapidly, while the photons were already on their way. This mattered for a very human reason. It makes pre-planning harder to imagine. A local hidden variable model that depends on knowing the measurement settings in advance begins to look strained when the settings are changing at the last moment. The photons would need instructions flexible enough to handle surprise questions that weren't even decided until the photons were in flight. Technically, what Aspect did involved switching between different analyzer configurations quickly, using devices that could redirect the photons through different measurement pathways. The details can get intricate, but the spirit is simple. The measurement is no longer a slow, announced decision. It becomes a sudden one. And once again, the results violated Bell's inequality. So, at that stage, the experimental story took on a new tone. It wasn't only, we see the violation. It was, we see the violation even when we make the measurement choice dynamic, even when we take steps to prevent the settings from being quietly coordinated. It's worth pausing on what this does and does not mean. It does not mean that one photon sends a signal to the other. It does not mean information travels faster than light. If it did, we'd be able to exploit entanglement as a faster-than-light messaging system, and we can't. The outcomes on each side are still random on their own. It's only when you compare them later that the correlation appears. What the experiments do mean is something quieter and more unsettling. Nature produces correlations that do not fit inside any worldview that insists on both locality and predetermined realism at the same time. Bell forced a choice. Experiments began to squeeze the available room where alternative explanations could hide. Still, a careful scientist could say, fine, but how fast is fast switching really? Are we truly closing locality? And what about detection? What about the photons that never get counted? Those are not nitpicks. Those are the difference between a striking hint and a settled result. This is why the history of entanglement experiments feels, in hindsight, like a slow tightening of a knot. First, you show the violation under reasonable conditions. Then you ask, could a clever classical model still slip through? Then you redesign the experiment to make that slip harder. Then you redesign it again. The early tests, Friedman and Clauser and others who followed, gave physics the first solid push into Bell's territory. Aspect's work added a new layer of discipline, showing that even with changing settings, the quantum signature persists. By then, entanglement was no longer a rumor. It was becoming a reliable feature of the world. But physics is patient. It likes the kind of certainty that comes only when you close more than one door at once, when you stop leaving the universe and out. So the next step was obvious and also difficult. Build experiments that close the major loopholes together in the same run with the same data. Not just, we think it's fine, but we designed it so it can't be fine unless nature really behaves this way. That push toward what people now call loophole-free tests was the gold standard the field kept moving toward. And once we reach that era, the story changes again. Because the question stops being, can entanglement violate Bell? And becomes, how far can we stretch this phenomenon? Across cities, across satellites, across larger and larger systems, until it feels less like a laboratory curiosity and more like a foundational thread of reality. After Aspect, the shape of the answer was starting to show itself. The numbers kept leaning the same way. But physics has a particular kind of stubbornness. It doesn't just want an answer that seems right. It wants an answer that leaves fewer and fewer places to hide. Because if you're skeptical, and in science, skepticism is a form of love, you can always ask two quiet questions. Did we really test all the pairs, or only the ones our detectors happen to notice? And did we really choose the settings late enough? Or could the experiment, in some ordinary way, have known them in advance? Those questions became the obsession for the next generation of entanglement tests. Not as an attempt to rescue the classical picture, but as an honest attempt to stress the quantum picture until it either cracked or held. By the mid-2010s, a milestone arrived. Experiments that were designed to close the major loopholes at the same time, in the same run, especially the two that mattered most for the argument. On one side was the locality concern, the insistence that no influence can travel faster than light. These newer tests arranged the timing so that the measurement choices and the measurement outcomes were separated in a way that left no room within ordinary spacetime for a message to coordinate them. On the other side was the detection concern, the worry that missing events could bias what we see. Different experiments approach this in different ways, using systems with higher detection efficiency, or architectures where the fair sample assumption becomes less and less reasonable to doubt. What matters for our sleepy journey tonight isn't every technical detail of how each group engineered it. What matters is the feeling of the knot tightening. When you close one loophole, you can still imagine the other one doing the mischief. When you close both, the imagination gets quieter. The classical escape routes don't vanish because someone declares them gone. They vanish because the experiment has fenced them off. And when those loophole-free results came in, the conclusion didn't land like a thunderclap. It landed like a door clicking shut. Not dramatic, final. At that point, is entanglement real? Stops being the main question. The better question becomes, how real is it? How far does it go? How much can we do with it before the ordinary world rubs it away? Because entanglement is not just a philosophical troublemaker, it's a physical resource, like energy, like coherence, like information. You can create it, you can spend it, you can lose it. So, researchers began to treat it less like a debate and more like something you can build with. That's when the experiments started leaving the lab. Not in a poetic sense, in a very literal one. Entangled photons were sent through fiber optic cables under cities. They were transmitted across open air between buildings. The distances stretched from rooms to campuses to kilometers, to networks that began to resemble the early outlines of what people sometimes call a quantum internet. And when you push entanglement outward like that, you begin to notice something that's both practical and almost tender. The world is loud. Light scatters. Fibers absorb. Temperature drifts. Vibrations whisper through equipment. Even the atmosphere itself becomes a shifting lens. And through all of that noise, you're asking for a delicate relationship, an invisible coordination between two quantum systems. Sometimes, when people first hear about long-distance entanglement, they picture a permanent bond, like a cosmic string tying particles together no matter what happens. But real entanglement is more like a candle flame in a drafty room. It's not that the flame isn't real, it's that it takes care to keep it lit. This is one reason satellite experiments became so compelling. If the problem on the ground is loss, photons absorbed in fiber, scattered in air, then a satellite gives you a different geometry. A large portion of the path can be through space, where light travels cleanly, and only the final segment cuts through the atmosphere. The engineering is demanding, the alignment is demanding, the timing is demanding. But the underlying message is simple. Entanglement isn't trapped at human scales. It can be distributed, shared, compared, and used over distances that make the two particles on a bench picture feel small. And once you see that, another idea becomes natural. If entanglement can be created and distributed, then it can also be connected, extended like a chain, not by stretching one entangled pair until it snaps, but by creating separate pairs and then linking the ends through clever protocols. This is the basic intuition behind repeaters and swapping, the infrastructure you'd need if entanglement is ever going to behave like a utility instead of a curiosity. You don't need to memorize the circuitry to feel the implication. If you can move entanglement around like this, you're not just confirming quantum mechanics. You're learning how to live inside it. And the moment entanglement becomes something you can route, people begin to ask a different kind of question. If it's so fragile, why does it show up so reliably? Because it does, again and again, in different platforms, in different laboratories, under different assumptions, across different distances. And then, just when your mind starts to feel comfortable, when the story begins to settle into, okay, it's photons, it's optics, it's delicate but manageable, physics does what it loves to do. It broadens the claim. Entanglement is not only a feature of light. It appears in atoms and ions. It appears in superconducting circuits. It appears in systems that look, at first glance, too warm and too messy to cooperate. In recent years, people have even produced evidence of entanglement in places that feel almost comically far from the original EPR thought experiment, high-energy particle collisions, where short-lived particles flash into existence and vanish again, yet still display correlations that fit the entanglement story. You don't have to hold on to every example. The important thing is the pattern. Entanglement isn't a trick of one special setup. It's a behavior the universe is willing to produce wherever the conditions allow it. And that raises a quiet but powerful shift in perspective. At first, entanglement feels like a weird connection between two objects. Then it starts to feel like a rule about information. What can be known, what can be predicted, what can be assigned as already real before a measurement. And eventually it begins to feel like a rule about reality itself, that the world does not always come in neatly separated pieces. Sometimes the most faithful description is shared, spread out, relational. Not spooky in a supernatural way. Spooky in the way a deep truth can be spooky, because it refuses to fit inside the boxes we inherited. So by now, after the loophole-free era and the long-distance demonstrations and the expanding platforms, it's fair to say the universe has answered Bell's question. Not with a lecture, with a consistent signature, stamped into experiment after experiment. Entanglement holds. And yet, there is one more twist, one that matters if we want to understand what this phenomenon means in the world we actually inhabit. Because if entanglement is so real, why don't we notice it everywhere all the time? Why does it vanish the moment things get warm, or large, or ordinary? Why does it feel like it belongs to laboratories and not living rooms? That brings us to the practical enemy, the quiet force that doesn't argue with entanglement, but simply dissolves it. Not through drama, through contact, through noise, through the simple fact that everything touches everything else. So it's real, and now we face the practical enemy. Even after decades of debate, the experimental story leaves us with a calm, stubborn conclusion. Entanglement is not a rumor. It shows up in the numbers. It survives careful tests. And it behaves the same way, again and again, in labs all over the world. But the moment we step outside those protected rooms, outside the cold hardware, the vacuum chambers, the carefully timed lasers, entanglement starts to feel like a fragile kind of luck. Not because it was never real, but because the world is busy. This is where we meet decoherence, the quiet enemy. To understand it, it helps to picture entanglement not as a permanent bond, but as a delicate pattern. A relationship written in phase, like two waves that stay perfectly aligned, crest with crest, trough with trough. When that alignment holds, the quantum state can act as one shared thing, even across distance. Decoherence is what happens when that pattern gets copied into the world around it. Not copied the way you copy a file. Quantum states can't be cloned like that, but copied in a softer sense, like the way a secret stops being a secret once a room starts to whisper it. The environment doesn't need to know the whole answer. It only needs enough clues, enough scattered hints, to make the quantum relationship effectively unreadable. In everyday life, everything is constantly touching everything else. Air molecules collide, light bounces, surfaces vibrate, heat stirs atoms into motion, and every one of those tiny interactions is a kind of question being asked. Where are you? Which way are you moving? What phase are you in? Which path did you take? In a quantum system, the most precious thing is often not the outcome, but the coherence, the clean, well-defined phase relationship that lets possibilities interfere with each other. That coherence is what makes superposition feel like a real physical resource rather than a poetic idea. Decoherence is the loss of that resource. And here's the strange part. In many cases, nothing is destroyed in the dramatic sense. There isn't a loud snap. There isn't a visible break. Instead, the quantum system becomes entangled with the environment in an uncontrolled way. A clean entanglement, two particles sharing one story, turns into a messy entanglement. Those particles sharing a story with countless stray photons, nearby atoms, electric fields, tiny vibrations in the apparatus, and the heat of the room itself. So the system doesn't become less quantum underneath. It becomes quantum in a way that's spread out into everything. That spreading is the problem, because once the environment carries which state information, once it holds even a faint record of what happened, the different branches of the superposition stop being able to interfere. They stop being able to overlap in a way we can access. The interference pattern doesn't vanish because nature changed its mind. It vanishes because the information leaked out into too many places. It's like trying to listen to a duet while 1,000 radios are turned on around you. The duet is still playing, but it's drowned in the noise of the larger world. This is why, when people ask, why don't we see quantum weirdness in everyday objects? The most honest answer isn't because quantum rules stop. The answer is, everyday objects are never alone long enough. A dust grain in a beam of light is being hit by photons constantly. Your coffee mug is shaking with thermal motion. The atoms in your hand are exchanging heat with the air. All of that interaction acts like continuous monitoring, not a conscious observer, just physics doing what physics does. In that sense, decoherence is like a natural drift toward the classical world. Not because classical reality is more fundamental, but because classical reality is what quantum systems look like when their delicate relationships have been smeared into the environment, when the phase information has become effectively inaccessible. And this connects to something quietly profound. Many people imagine measurement as a special moment, an event where the universe chooses. Decoherence shows us a different perspective. A lot of what feels like measurement is simply entanglement with the surroundings. A system becomes correlated with its environment. The environment becomes correlated with still more of the environment. And very quickly, the quantum state becomes so widely shared that for all practical purposes, it behaves like a single definite outcome. If you ever hear someone say, decoherence explains the collapse, it's worth holding that gently. Decoherence explains why superpositions stop behaving like superpositions to us, why interference disappears, why outcomes become stable, why the world looks classical. But it doesn't by itself answer every philosophical question about what really happens. What it does give us is a reason quantum technology is hard. Because entanglement isn't just a concept, it's a condition. It's a state of delicate coordination. And coordination is easy to lose when everything around you keeps bumping the table. This is why quantum experiments love cold temperatures. They love isolation. They love vacuum. They love shielding. They love quiet. Not because physicists are dramatic, but because heat is motion, and motion is interaction, and interaction is information leakage. And once the information leaks, the special togetherness of entanglement starts to unravel. Yet here's the hopeful turn. Decoherence is not a verdict. It's not the universe banning entanglement from the real world. It's simply the price of doing quantum work in a noisy cosmos. And over the last few decades, we've learned how to pay that price carefully. We've learned how to cool systems down until thermal noise becomes a whisper. We've learned how to trap ions in near-perfect isolation. We've learned how to guide photons through fibers and space. We've learned how to design devices where the environment is kept at a respectful distance. And perhaps most importantly, we've learned a counterintuitive lesson. Even when you can't make the world perfectly quiet, you can still build machines that keep the quantum pattern alive long enough to be useful. Because once you can preserve entanglement, even briefly, you can turn it into something practical, not magic, a tool, a kind of engine. After you understand decoherence, quantum computing stops sounding like a flashy promise and starts sounding like a very particular kind of engineering challenge. Because a quantum computer isn't a faster computer in the usual sense. It's a machine built to protect a fragile kind of relationship long enough to do work with it. And that relationship, again and again, is entanglement. A classical computer runs on bits. A bit is confidently one thing at a time, a 0 or a 1. You can stack billions of them together, and the machine's job is to flip those bits with reliability. Even when there's noise, the logic is solid. Each bit has a definite value, and you can copy it, check it, store it, and send it. A quantum computer runs on qubits. A qubit can behave like 0 or 1, or a blend of both, described by probability amplitudes. That's the part people hear first, and it sounds mystical. But superposition alone is not the whole engine. If you have one qubit, its blend is simple. 2 qubits are more interesting. 3 qubits are more interesting still. And then something quietly dramatic happens. As you add qubits, the full description of the system becomes too large to write down in any straightforward way. Not because the universe is trying to hide it, just because the math grows extremely fast. This is where entanglement enters like a hidden gear. If qubits were only independent coins, each one flipping privately, the story would still be manageable. You'd have separate probabilities for each qubit, and the whole system would be just a pile of parts. Entanglement is what makes the pile act like a single object. It ties the qubits together so that you can't fully describe one without referencing the others. The system becomes a shared state, a single fabric rather than a bundle of threads. And once you have that fabric, you can do something a classical computer can't do in the same direct way. You can shape a computation that lives in the structure of the shared state itself. That's the dream. But it's also the difficulty. Because to get a useful quantum computer, you don't want random entanglement. You want controlled entanglement, created on purpose, steered on purpose, and kept clean long enough to matter. In practice, quantum computers create entanglement using specific operations, especially 2-qubit gates, the interactions that let one qubit state depend on another's. These are the moments where the machine stops being a collection of isolated qubits and becomes a coordinated system. And when those gates work well, something remarkable becomes possible. Interference can be guided. That word, interference, is the quiet heart of why quantum algorithms can outperform classical ones for certain tasks. The quantum state isn't just many possibilities. It's many possibilities with phases, meaning the amplitudes can add or cancel like waves. A good quantum algorithm is less like trying everything at once, and more like arranging waves so the wrong answers cancel themselves. Entanglement helps that arrangement scale. It allows correlations across many qubits so that the cancellations and reinforcements happen in a high-dimensional space a classical computer can't easily mirror. This is why the most famous quantum algorithms are often described in terms of a dramatic payoff. Shor's algorithm is the classic example. It shows that a large enough error-corrected quantum computer could factor certain big numbers efficiently, numbers that form the backbone of some widely used cryptography. That doesn't mean all cryptography breaks overnight, but it does mean the mathematical terrain changes. It's one of the reasons people talk seriously about post-quantum cryptography today. Grover's algorithm is a different kind of speed-up. It's a square-root acceleration for searching an unstructured space, less explosive than Shor, but broad in spirit. It suggests a general rule. Quantum mechanics can sometimes give you a systematic edge, not by magic, but by wave behavior disciplined into computation. And in both cases, entanglement sits in the background like a power line, not always flashy in the headline, but crucial to running the machine at scale. Now, it's also important to keep the tone honest. The quantum computers we have today are real. They run circuits, they create entanglement, they demonstrate algorithms and experiments, but they're also noisy. The qubits lose coherence, the gates are imperfect. The environment leaks information in exactly the way we talked about earlier. So, when you hear the phrase quantum advantage, it helps to imagine a very specific, narrow kind of victory. A particular task, performed under particular conditions, where the quantum machine does something hard to replicate classically. That's not a disappointment, that's what early technology looks like. The first planes didn't carry cities, they proved a principle. They taught engineers what air demands. Quantum computing is in its what does nature demand era. And nature demands three things at once. First, the qubits need to be controllable, so you can prepare states reliably, apply gates precisely, and read out results. Second, the qubits need to be connected, so entanglement can spread across them in the patterns your algorithm requires. Third, the whole system has to be protected, so decoherence doesn't smear those patterns into the environment before the computation finishes. Different hardware approaches make different trade-offs here. Some systems have qubits that are very clean but harder to scale. Others scale more easily but struggle with noise. Some use trapped ions where qubits can be extremely uniform. Some use superconducting circuits where gates can be fast and fabrication can leverage chip-making techniques. Photonic approaches push information along light itself. Neutral atoms offer elegant arrays. It's not one road, it's many roads, all trying to solve the same puzzle. How do you build a machine that stays quantum on purpose? And the deeper puzzle is this. Quantum computing power isn't simply more qubits. It's more good qubits working together with enough high-quality entanglement to perform meaningful interference before decoherence takes it away. That's why you'll often hear researchers talk about fidelity, error rates, and circuit depth. Those words are not marketing. They're the daily reality of making entanglement behave like an engine instead of a spark. Because if a computation needs a long chain of entangling operations, each tiny imperfection compounds. The delicate wave pattern that's supposed to cancel wrong answers begins to blur. Instead of sharp interference, you get washed out statistics. The quantum result starts to look like noise. So, the field has learned to value something almost poetic in its restraint, keeping quantum states alive just long enough. And even before fully error-corrected, large-scale machines exist. This effort already feeds into real science and engineering. Quantum computers are used as testbeds for simulating small quantum systems, chemistry, materials, magnetic models, places where nature itself is quantum, and classical simulation becomes expensive. The goal isn't replace all computers, but build a specialized instrument, like a microscope for quantum behavior. In that sense, a quantum computer is closer to a laboratory device than a laptop. It's a controlled environment where entanglement can be grown, shaped, measured, and studied. And when you view it that way, the story becomes cleaner. Entanglement is not just something we argue about in philosophy. It becomes a working fluid, like electricity in a circuit or pressure in an engine. You can generate it, you can route it, you can waste it, you can protect it, you can spend it to accomplish a computation. And just like any working fluid, the true art is learning how to manage losses. That brings us to the biggest obstacle that also becomes the biggest idea. In classical computing, you handle errors by copying information and checking it. You store backups, you repeat bits, you run parity checks. You rely on the fact that you can look at a bit without destroying what it is. In quantum computing, you don't get that luxury. You can't copy an unknown quantum state. You can't peek at a qubit whenever you want without changing it. The very thing that gives quantum computing its power, the coherence, the phase, the delicate superposition, also makes it vulnerable to inspection. So, if you're going to build a quantum computer that scales, you need a way to protect information without copying it and without constantly collapsing it. A way to detect errors while keeping the quantum message intact. A way to heal without making a duplicate. And that is where the next idea becomes beautifully counterintuitive. A quantum computer, at its core, is a promise that feels almost unfair. It says, we will keep a delicate quantum pattern alive long enough to use it. And then it immediately runs into a rule that feels equally unfair. In the classical world, if you're worried about errors, you make copies. You duplicate a file, you write the same bit 3 times, you compare, vote, correct, move on. Reliability is built from repetition. Quantum physics doesn't let you do that. If a qubit is carrying an unknown quantum state, you can't simply copy it perfectly. That isn't a limitation of our tools. It's a rule of the theory itself. The no cloning principle is nature's way of saying, a quantum state is not a photograph you can duplicate. It's closer to a living wave pattern, and perfect copying would break the logic that makes quantum mechanics consistent. So the question becomes, how do you protect something you're not allowed to copy? That question gave birth to one of the most beautiful ideas in modern physics and engineering, quantum error correction. It works by changing what you mean by a qubit. Instead of storing information in a single physical qubit, you spread one logical qubit across many physical qubits, like a message written not in one letter, but in a whole sentence. No single qubit carries the full story. The information lives in the relationships among them, and those relationships are made of entanglement. This is the key shift. Quantum error correction doesn't try to keep each qubit perfect. It accepts that qubits will suffer small slips, tiny rotations, little phase drifts, occasional flips, because the real world is warm, noisy, and impatient. Instead, it builds a structure where errors can be noticed without reading the secret itself. In classical error correction, you check the bits directly. In quantum error correction, you measure special, parity-like quantities, often called syndromes, that tell you something went wrong and even hint at what kind of wrong it was, without forcing the underlying quantum information to reveal itself. It's like walking through a dark room and noticing a floorboard creaked, without turning on the lights and without seeing what's inside the room. You get a clue, not a confession. And those clues are enough, because many common quantum errors can be treated as combinations of just a few basic types: bit flip-like errors, phase flip-like errors, and mixtures of both. Error correction turns the chaos of the environment into a small alphabet of mistakes you can track. Then comes the part that sounds almost like a paradox until you sit with it. You measure in order to avoid collapsing the computation, but you measure only the right things. You measure the presence of error, not the value of the quantum message. That distinction is what makes scaling possible in principle. Now, once you have the idea of a logical qubit protected by entanglement and syndrome checks, you can start to see why people talk about fault-tolerant quantum computing as a threshold dream. It's not that errors disappear, It's that errors can be corrected faster than they accumulate. Like bailing water from a boat, it's fine to have leaks, as long as you can bail faster than the ocean can fill you. This is also why the road to a large quantum computer is paved with a specific kind of patience. The hardware doesn't just need more qubits, it needs better qubits, connected in ways that allow repeated entangling operations, repeated syndrome measurements, and repeated corrections over and over without the whole system unraveling. And that brings us to architectures, because the physical design of a quantum computer is, in many ways, a design for entanglement logistics. Different platforms, superconducting circuits, trapped ions, neutral atoms, photonics, each offer different strengths. Some provide fast local operations, some provide clean, long-lived qubits, some connect qubits through light. Some place qubits in neat grids like a chessboard, but no matter the platform, the same practical questions keep returning. How do we entangle qubits reliably? How do we connect enough of them without introducing more noise? How do we measure syndromes quickly without disturbing the protected state? How do we keep the wiring, control signals, and readout from becoming their own source of decoherence? The architecture is the answer to those questions in physical form. That's why so many leading approaches lean toward layouts that look almost ordinary. Grids, tiles, repeating patterns. It's not because physics is boring. It's because error correction likes order. It likes a geometry where checks can be applied locally, repeatedly, and predictably. A famous example is the surface code family of ideas, where qubits are arranged on a 2D lattice and error checks are performed on neighboring groups in a repeating rhythm. You don't have to memorize the details to feel the intuition. The information is stored in a kind of woven fabric, and the error checks are the gentle tug that keeps the weave from slipping apart. When this fabric is working, the entanglement in the machine isn't just a computational resource anymore. It becomes protective scaffolding. It's entanglement used not to do something flashy, but to keep something fragile from dying. And this is why quantum computing is often described, quietly, as an argument for humility. Because the most powerful thing we know how to do with entanglement is not to send messages faster than light, and not to summon science fiction. The most powerful thing is to build a system where quantum weirdness can survive long enough to be useful. A stable island of coherence inside a noisy sea. If you've ever wondered why the timelines in quantum computing feel both exciting and slow, this is the reason. We're not just building faster logic gates, we're building a shelter for a mathematical pattern that the universe is constantly trying to blur. And yet, we've learned to shelter it. We've learned to detect errors without stealing the secret. We've learned to correct without copying. We've learned to keep a wave intact by listening only to its bruises. And once you accept that this is possible, even in principle, the story of entanglement changes again. Because if computing is one kind of power, error correction is a different kind of power. It's the power to make a quantum state reliable. And when a quantum state becomes reliable, it can become something else too. Well, not just a tool for computation, but a tool for trust. In the ordinary world, security is a math problem. You lock a message with a key, and you trust that no one has the time or the computing power to guess their way in. The safety comes from difficulty, from the hope that some problems stay hard long enough to matter. Quantum cryptography begins with a different kind of safety, one that doesn't rely on hope. It starts with a quiet observation. In the quantum world, listening leaves fingerprints. Not the kind you see with a microscope, but the kind the laws of physics refuse to hide. Imagine a single photon traveling down a fiber optic cable. It isn't a tiny marble with a label on it. It's closer to a fragile question the universe is carrying from one place to another. If you try to peek at it in the middle of its journey, you don't just copy down what it says. You change what it becomes. That fact is usually introduced as a philosophical puzzle. In quantum cryptography, it becomes practical, because an eavesdropper, someone tapping the line, can't take a perfect look and leave everything untouched. There's no invisible spy camera that can watch a quantum state without interacting with it. In the simplest picture, The act of measuring forces the photon to choose a definite outcome, and that choice tends to scramble the delicate correlations that were supposed to be shared only between the sender and the receiver. So, for once, the weakness becomes the shield. The core idea behind quantum key distribution, QKD, is not to send a secret message directly in quantum form. Instead, you use quantum states to build a shared secret key. Then you use that key to encrypt ordinary messages in the familiar way. It's a two-step dance. First, two people, traditionally called Alice and Bob, send quantum signals and collect outcomes. The signals are prepared in ways that make eavesdropping detectable. Then, after the quantum exchange, they talk openly over a normal classical channel. They compare some of what they did, they discard the parts that don't line up, and they test for disturbance. If the disturbance is too high, they don't argue about who might be listening. They simply assume someone is. They throw the key away and start again. If the disturbance is low enough, they do something that feels almost like cleaning a photograph. They correct minor mismatches, they shrink the information that an eavesdropper could have gained, and what remains is a shared key that's private for a reason deeper than computation. Private because physics won't let it be otherwise. There's a gentle way to picture what's happening. Alice is not trying to mail Bob a locked box. She's sending a stream of tiny coin flips, but each coin flip is wrapped in a choice of how it will be flipped. One moment, it's a coin that can land heads or tails. The next moment, it's a coin that can land left or right. Those two descriptions don't peacefully overlap. They're different ways of asking the photon a question. Bob, at the other end, also chooses which question to ask. Sometimes he matches Alice's choice, sometimes he doesn't. When the choices match, the results can be used. When they don't, the results are thrown away. And here's where the protection lives. An eavesdropper in the middle doesn't know which question is the correct one at the moment of interception. If they guess wrong, their measurement introduces errors. If they try something more clever, the quantum rules still squeeze them. Information gained tends to create disturbance. That disturbance becomes visible when Alice and Bob compare a small sample of their results. It's like two people comparing a few notes from a long melody. If someone has been plucking at the strings in the middle, the harmony won't quite hold. Now, none of this requires faster-than-light messaging. None of it requires mystical mind reading between particles. The security comes from the same quiet truth we've been circling all night. Quantum states are not passive objects. They are sensitive descriptions of possibility, and touching them matters. That's why QKD is often described as security guaranteed by the laws of physics. Not guaranteed in the sense that nothing can ever go wrong. Real systems have imperfect detectors, noisy channels, side channels, and implementation mistakes. Engineers worry about blinding attacks, timing leaks, and the messy ways real hardware can betray a clean theory. But the foundational promise is still remarkable. If you implement it correctly, an attacker cannot copy the quantum signal perfectly. An attacker cannot measure it perfectly without leaving traces. And an attacker cannot hide those traces forever because the users are actively checking for them. In classical cryptography, you might never know you've been breached until it's too late. In the quantum version, the breach tries to announce itself. And once you feel that, you can see why people dream about quantum networks. If you can distribute keys with physics-level security, you can build links between banks, hospitals, governments, research labs, anywhere secrets matter. You can imagine a world where sensitive communications don't rest on the assumption that today's math will stay unbroken tomorrow. Because even if computers get stronger, the quantum rule stays the same. You can't steal a quantum key without nudging it. You can't listen without leaving a scar. And in a universe where so many things are uncertain, that's a strangely comforting kind of certainty. It's also a bridge. Because once you start talking about sending quantum states through fibers, through free space, across cities, even between satellites and ground stations, you're no longer just doing cryptography. You're practicing the art of moving quantum information across distance. You're learning how to keep fragile correlations intact while the world tries to shake them apart. And when you take that next step, when you try not just to share a key but to share a state, a familiar science fiction word starts to drift into the conversation, not as a fantasy, as a careful technical procedure: teleportation. Teleportation is one of those words that arrives with a suitcase full of science fiction. It makes you picture a person dissolving into glitter, then reappearing somewhere else, perfectly intact. But quantum teleportation is quieter than that. Nothing gets yanked through space. Nothing outruns light. What changes is something more subtle: the state of a quantum system, the way it would behave if you measured it. To feel what that means, imagine a small melody you can't record. You can hum it, you can recognize it, but the moment you try to capture it exactly, you alter it. A quantum state is like that. It's not a secret code you can copy and paste. In fact, quantum physics has a strict rule, often called the no cloning principle, that says you can't make a perfect duplicate of an unknown state. You can't scan a qubit and print a fresh one. And yet, teleportation somehow seems to do exactly that: make a state appear somewhere else. The trick is that teleportation isn't copying, it's moving a state by consuming a shared link that was prepared ahead of time. That shared link is entanglement. Picture two particles that were created together and then separated. They are like two halves of a single promise. Each half, on its own, looks random, but together, their outcomes are stitched into one pattern. That pattern is the resource teleportation spends. Now add a third particle, call it the message particle, not because it carries a normal message, but because it holds the quantum state we want to transfer. Maybe it's a photon polarization, maybe it's a qubit in a chip. The details can change, but the logic stays the same. Here's the calm, slightly mind-bending sequence. First, two distant labs share an entangled pair. One half sits with Alice, the other half sits with Bob. They might be on opposite sides of a building, or separated by miles of fiber, or even farther. The entanglement is already in place before any teleportation begins. Next, Alice takes the message particle, the one with the unknown state, and performs a special joint measurement on it together with her half of the entangled pair. This is the key move. She is not measuring the message particle alone, because measuring it alone would force it into a definite outcome and destroy the very thing she wants to transfer. Instead, she measures a relationship between the two particles in her lab. That measurement produces a small, ordinary result, just a few classical bits of information, not a full description of the quantum state, just a label: this outcome, or that outcome. The result is random because quantum outcomes are random. But once the result exists, something remarkable is true. Bob's distant particle is now related to the original message state in a precise way. Not identical yet, related. At this point, if Bob does nothing, his particle is in the wrong orientation, so to speak. It's like a compass that points in the right direction, but rotated. The rotation depends on which measurement outcome Alice obtained. So Alice sends her ordinary classical bits to Bob through a normal channel that can't beat the speed of light. A phone call, a fiber optic line, anything classical. When Bob receives those bits, he performs a simple correction, one of a small set of possible adjustments. And after that correction, Bob's particle ends up in the exact state that Alice's message particle had at the beginning. The state has arrived. And here's the part that keeps the universe honest. The original state is gone from Alice's side. The joint measurement doesn't preserve it. Teleportation doesn't produce two copies. It produces one surviving instance, relocated. So, quantum teleportation doesn't violate relativity because Bob can't complete the process until the classical information arrives at light speed or slower. And it doesn't violate no cloning because the original is not retained. It's a transfer that spends entanglement like fuel. If teleportation is the sci-fi word, super-dense coding is the sci-fi punchline. Super-dense coding flips the story. Instead of moving an unknown state, it uses entanglement to pack more classical information into a smaller quantum transmission. Normally, if you want to send two classical bits, say As a 1, 10, 11, you need a system with 4 distinct, reliably distinguishable states. With a single classical bit, you only get 2 possibilities. But if Alice and Bob share an entangled pair in advance, Alice can manipulate her half in one of 4 simple ways, each corresponding to one of those 2-bit messages. Then she sends her single particle to Bob. When Bob receives it, he performs a joint measurement on the 2 particles together. Because the pair began entangled, the combined system can reveal which of the 4 manipulations occurred. 1 particle sent, 2 bits received. It sounds like cheating until you remember the cost. The entanglement had to be created and distributed earlier. The extra capacity isn't appearing from nowhere. It's being drawn from a resource that was patiently prepared in advance. Teleportation and superdense coding are like 2 faces of the same idea. Entanglement can be stored, transported, and then cached in later for capabilities that classical physics can't imitate. And that leads naturally to the next challenge: distance. Entanglement is fragile. Photons get absorbed, fibers lose light, noise creeps in. Over long stretches, the entangled link fades into ordinary, unhelpful randomness. This is where entanglement swapping enters, and it's one of the most elegant moves in all of quantum information. Imagine you want Alice and Bob, far apart, to share entanglement, but you can only distribute entanglement reliably across shorter links. So you create 2 entangled pairs. One pair connects Alice to a middle station, and another connects the middle station to Bob. The middle station holds 1 particle from each pair. Now the middle station performs the same kind of joint measurement we described in teleportation on its 2 particles. That measurement doesn't send anything faster than light. It simply rewires the correlations. After the measurement, Alice's particle and Bob's particle, particles that never interacted, become entangled. Entanglement has been swapped across the gap. Do this in a chain, and you can extend entanglement step by step, like lighting lanterns down a long road. In practice, building a quantum repeater is hard because you need memory that can hold quantum states, and you need operations that are clean enough to keep entanglement from washing out. But conceptually, it's stunningly simple. You can stitch short quantum links into longer ones by performing careful measurements at the joints. So, when people talk about a quantum internet, they don't mean streaming movies via entanglement. They mean a network whose backbone is made of shared quantum states, distributed entanglement that can support teleportation of qubits, secure key distribution, and new kinds of sensing and synchronization. And if you step back, you can feel the thread running through all of it. Entanglement isn't a signal. It isn't a mysterious force. It's a kind of structure, a relationship that can be prepared, moved, degraded, repaired, and used. Teleportation shows that a quantum state can be relocated without ever being read. Superdense coding shows that pre-shared relationships can amplify what a single particle can carry. Swapping shows that distance is negotiable if you're willing to build the bridge in segments. And in the next stretch of our journey, we'll lean into a calmer, practical question. If entanglement is so powerful and so delicate, how do we keep it alive long enough to do real work? Entanglement doesn't only let us move delicate quantum states from one place to another, it also changes what it means to look at the world. In everyday life, measurement feels simple. You shine a light, you count something, you read a number, and if you want a clearer answer, you usually do the same thing again. More light, more time, more samples. But at the deepest level, nature charges a kind of fee for information. Not a moral fee, not a punishment, just a quiet trade. The more precisely you try to extract certain details, the more other details blur, or the more graininess creeps in through the physics of the measurement itself. This is where the quantum eye comes in. Most of the time, the limit on precision is not your engineering. It's not the quality of your lens or the stability of your tripod. It's something more fundamental, the randomness built into the particles you use to measure. If you measure with light, you measure with photons, and photons arrive like raindrops. Even if your average brightness is steady, the exact arrival times wobble. Count them for 1 second, then count them again, and you'll get slightly different totals. That is not a mistake. That is the texture of the universe. Physicists have a gentle name for this kind of limit: shot noise. It's the jitter you get when your measuring tool comes in discrete packets. You can reduce shot noise by using more photons, more raindrops. The relative fluctuations shrink as your sample grows. That's the classic strategy. It's why longer exposure times help in photography, and why collecting more data tends to improve an estimate. But quantum mechanics offers a second strategy that feels almost like a secret passageway. Instead of only increasing the number of particles, you can change the relationships among them. You can shape the noise itself. This is where entanglement and squeezing enter the story, and the idea is beautifully simple, even if the math underneath is not. Imagine you're trying to measure a tiny shift, an almost impossible wobble, using a beam of light. The beam carries two kinds of uncertainty at once, like a coin with two faces. One side is the uncertainty you care about, the other is uncertainty you'd prefer to move somewhere else. In ordinary light, those uncertainties are balanced. You can't reduce both at the same time. But in squeezed light, you compress the uncertainty in one direction, making the measurement you care about cleaner, while the uncertainty expands in a direction you're not measuring, or not measuring as strongly. It's not breaking the rules, it's rearranging them. Entanglement takes that a step further, because it allows multiple particles to behave like a coordinated team, rather than independent coin flips. When the particles are linked, their random jitters are no longer separate. They can partially cancel. They can line up in ways that make a collective measurement sharper than any single particle could support alone. This is the heart of quantum metrology, using quantum structure, squeezing, entanglement, and carefully prepared correlations to beat the ordinary measurement limit. People sometimes describe two ceilings here. One is the common everyday statistical ceiling, shot noise. It's sometimes nicknamed the standard quantum limit because it's the best you can do if your particles are basically acting independently. The other is a more extreme ceiling you can approach with highly entangled resources, often called the Heisenberg limit. Don't let the word intimidate you. The intuition is simply that entanglement can let your precision improve faster with resources than it would with independent particles. In practice, it's hard to reach that ideal limit. The environment is noisy. Entanglement is fragile. Every real system leaks information to the outside world. So most real sensors live somewhere between those two ceilings, still classical looking in some ways, but with a quantum advantage quietly baked in. And this isn't only theoretical. One of the most famous demonstrations of the quantum eye is not in a small lab with a single tabletop laser. It's in one of the most sensitive listening devices humans have ever built: gravitational wave detectors. When LIGO listens for ripples in space-time, it's measuring a change so small that describing it feels like poetry, not engineering. A passing gravitational wave changes the length of LIGO's arms by an amount smaller than the diameter of a proton, an almost unthinkable precision. At that level, the detector isn't limited by sloppy mirrors. It's limited by quantum noise in the light itself, by photons arriving with that inevitable jitter. So, LIGO has used squeezed light to reduce one kind of noise in the band where it matters most. The result is not that the universe becomes quieter, it's that the instrument becomes better tuned to the right kind of quiet. It's a beautiful example of the theme we've been building. Entanglement and its close cousins don't create magic signals. They create structure, and structure can be traded for performance. Now, if that sounds abstract, there's another example that feels almost dreamlike, but is very real: ghost imaging. Ghost imaging sounds like a parlor trick, as if an image is being pulled out of nowhere, and in a way, that's exactly how it feels the first time you hear it. The basic idea is this: you can form an image of an object using photons that never actually touch the object. How? You generate pairs of correlated photons. They might be entangled, or they might be strongly correlated in a classical way depending on the setup. But the soul of the technique is correlation. One photon in each pair heads toward the object. On that side, you don't use a fancy camera. You might use a simple bucket detector that just tells you whether a photon arrived. No spatial information at all. The other photon in each pair goes to a high-resolution detector that does know where the photon landed, but that photon never went near the object. Now you compare the detection events. You correlate them. You keep track of which partner photon landed where when the bucket detector clicked. Over time, a pattern emerges. The image forms, not from the object side directly, but from the way the two streams of detections line up together. It's as if the image is assembled by a relationship rather than by a direct imprint. That's why it's so evocative for our story. Even if a given ghost imaging experiment uses classical correlations rather than strict entanglement, it still teaches the same lesson. Correlation can be an optical tool. Information can be extracted from joint structure, not from a single isolated beam. And once you start thinking this way, you begin to notice entanglement's fingerprints in places that feel surprisingly grounded. Consider time. We treat time like a background, something that flows and carries everything else along. But our most precise clocks don't measure time in a mystical way. They measure the ticking of quantum systems. Atomic clocks use atoms that oscillate at exquisitely stable frequencies. You lock a laser to the atom's transition and you count the cycles. That counting becomes timekeeping. The result is so stable that modern clocks would lose less than a second over an astonishing span. And here's where the universe gets quietly intimate. Gravity affects time. A clock at a higher altitude ticks a little faster than a clock lower down, because gravitational potential influences the rate at which time passes. That's general relativity. No drama, just reality. So, when atomic clocks become extremely precise, they don't only tell you the time, they can start to tell you about gravity. They can act as sensors. There's a growing field sometimes called quantum gravimetry and quantum sensing, where the goal is to map tiny variations in gravitational fields using quantum systems. Often atom interferometers, where matter waves take two paths and then recombine, and the phase difference encodes the influence of gravity or acceleration. In some of these setups, entanglement can improve the readout. In others, squeezing reduces noise. Either way, the pattern is the same. Quantum structure lets you see finer detail. It's easy to imagine practical uses: mapping underground cavities, monitoring subtle shifts in the Earth, improving navigation when GPS is unavailable, detecting faint signals that would otherwise drown in randomness. But beyond the applications, there's something emotionally strange about it. The most delicate ideas in quantum theory, ideas we once argued about in smoky rooms and chalk-dusted lectures, have become ingredients in instruments that feel almost bodily. Instruments that listen, that see, that keep time. This is where entanglement stops being only a philosophical discomfort and becomes a practical advantage. It becomes a technique, and it also changes a deeper intuition we carry around. We're used to thinking of measurement as something local. I shine light here, and I learn about what's here. But the quantum eye teaches a different lesson. Sometimes the best information about a system is not contained in one place. Sometimes it lives in the relationships between places. Sometimes the sharpest picture comes from comparing two streams of events that, on their own, look like noise. When correlation becomes a tool, meaning starts to shift. And that sets the stage for the more reflective question waiting just ahead. If experiments force us to accept these non-classical relationships, what exactly is the universe asking us to give up? Locality, realism, or some quieter assumption we didn't even realize we were carrying? At a certain point, the story of entanglement stops sounding like a strange trick that happens to particles and starts sounding like a question asked directly to us, not to our emotions, to our assumptions. Because Bell's theorem doesn't merely say, quantum mechanics is weird. It says something sharper and calmer and almost unavoidable. If the world behaves the way the experiments suggest, then at least one of our favorite classical instincts has to loosen its grip. To make that clear, it helps to name the instinct Bell targeted: Physicists often bundle it into two words: local realism. Local is the comforting idea that influences don't leap across space faster than light. If something changes here, it shouldn't instantly force a change over there, with no time to travel. Space should matter. Realism, in this context, is the idea that physical properties exist in a definite way even when no one is looking. The particle has a value, we just haven't checked it yet. Measurement reveals. It doesn't create. Together, local realism is the old picture that reality is made of local pieces with pre-existing features. Bell showed that picture can't fit the full set of quantum correlations. Not if we also trust a few basic principles, like the idea that the settings chosen on one side aren't secretly controlled by hidden coordination with the other side. And what makes this so haunting is how gentle it is. Bell didn't add mystical ingredients. He took ordinary-looking assumptions and asked what they imply. His inequalities are like rails on a staircase. If you start here and accept these steps, you can only arrive at certain landings. Quantum mechanics predicts a landing that local realism can't reach. So, when experiments violate Bell's inequality, it's as if nature is quietly saying, your map has to be redrawn. But what exactly do we redraw? Different interpretations answer that question in different ways. And here it's worth slowing down, because interpretations are often treated like philosophical decoration. In reality, they are attempts to explain what the mathematics means about the world. Quantum theory is extremely good at predicting outcomes. What it refuses to do, at least not in any single universally accepted way, is tell us what is happening in between. So, let's walk through the three most common storylines with a steady hand and without forcing a verdict. The Copenhagen-style view says the quantum state is not a simple photograph of reality. It's a tool for predicting probabilities. Measurement is not just another interaction. It's the moment where the question becomes meaningful in a definite way. On this view, it's not that the particle carried a hidden, pre-written answer the whole time. Instead, the answer becomes definite in the context of the measurement itself. This can feel unsatisfying at first, because we want the world to have properties the way a rock has weight, whether or not someone is watching. Copenhagen asks you to release that demand, at least for microscopic systems. It's not saying consciousness creates reality. It's saying the conditions of measurement are part of the physical description, and the theory doesn't promise more than that. Many worlds keeps the equations as smooth as possible. No special collapse, no sudden jump. The wave function evolves continuously, always. And when a measurement happens, the combined system, particle plus apparatus plus observer, enters a superposition of outcomes. Each outcome exists in a branch. You experience one branch as your world because you are inside it. Many worlds is often presented as dramatic, but the motivation is almost minimalist. Don't change the math. It trades one kind of weirdness for another. It rescues locality in a certain formal sense, because nothing needs to send a signal faster than light. Everything is just one big quantum evolution. But it asks you to accept that reality is larger than the single track of events you remember living through. Pilot wave theory, often associated with de Broglie and Bohm, takes a different route. It says particles really do have definite positions, and there is a guiding wave that steers them. The wave function is real, and it choreographs motion. In this story, the hidden variables are not about magic. They're about an additional layer of description. But there's a cost. The guiding wave is fundamentally non-local. The theory can reproduce quantum predictions, yet it does so by allowing a kind of global coordination. In Pilot Wave, the universe is stitched together by a deeper connection that doesn't respect the classical idea of separate independent parts. So, notice what's happening across these three perspectives. Copenhagen relaxes realism in the classical sense and treats measurement as a boundary the theory takes seriously. Many Worlds relaxes the uniqueness of outcomes, keeping the evolution local but enlarging what counts as real. Pilot Wave keeps definite properties but accepts a non-local structure underneath. Each one is a different way to respond to Bell's quiet challenge, and none of them changes the predictions you test in the lab. That's why this topic can feel like walking through fog. The ground under your feet is solid. Experiments, statistics, reproducible results. But the horizon is open. Now, once we accept that entanglement is not a glitch, a new kind of question appears. It's less about signals and more about meaning. If the world is built from correlations that don't fit the classical idea of independent parts, then perhaps independence is not the default state of reality. Perhaps relation comes first. This is where a modern phrase drifts into the conversation. It from qubit. The phrase suggests that physical reality, it, might be rooted in information-like structure, qubit, not in the sense that the universe is a laptop, but in the sense that the deepest description might be about what can be correlated with what can be known together, and what cannot. In a classical worldview, information is something we learn about an object. In an it from qubit flavored worldview, information is closer to something the world is made of. Patterns of distinction, constraint, and connection. Entanglement becomes more than a feature. It becomes a kind of architecture. And once you start thinking that way, another delicate thread appears. The question of free choice. Bell's analysis assumes that the measurement settings, like the angle of a polarizer, are not secretly prearranged to conspire with the particles. Physicists sometimes call this measurement independence or freedom of choice. It's not a moral claim, it's a structural one. The random choices we make in the lab should be statistically independent of the hidden details carried by the particles. If that independence fails, you can keep local realism, but only by accepting a kind of cosmic coordination so strong it starts to feel like the universe pre-wrote the experiment and the experimenters together. Some people explore that idea under the label superdeterminism. It's a logically possible escape route, but it's a steep one because it threatens the very method of experimental science. The idea that we can choose what to measure without the choice being secretly tied to the system under test. Most physicists don't reject it because it's forbidden. They reject it because it is hard to make it useful. It can explain anything by explaining everything, and once it does, prediction becomes slippery. Still, the reason it keeps returning is simple. Bell forces a trade, and people keep searching for the least painful currency. And now we arrive at a final, gentler idea. One that feels strange in the right way for a bedtime channel. The possibility that even time might be relational. There is a proposal often associated with Page and Wooters that goes roughly like this. If the universe as a whole is described by a quantum state, maybe there is no external ticking clock. Instead, what we experience as time is the way parts of the universe correlate with other parts. A clock is not a universal river flowing everywhere. A clock is a subsystem whose changing state can be compared with another subsystem. Time, in this view, is not painted onto the universe from the outside. It's an internal pattern, an ordering that emerges from correlations. You don't have to believe this idea to appreciate the mood it creates. It whispers a consistent theme. Maybe the most fundamental description is not about objects carrying private properties, but about systems holding relationships. And if that's true, then entanglement is not just a surprising connection between two particles. It's a hint about what reality considers basic, a hint that what we call space and separation might be a higher level story, something that appears when the web of correlations takes on a stable shape. So as we let the philosophical dust settle for a moment, keep one thought close and simple. Bell didn't make the universe mystical. He made it honest. He showed us that we can't demand all of our classical comforts at once. We can keep some. We can rebuild others. But we have to choose carefully what we mean by real. And once space and time start looking less like a stage and more like a consequence of thus deeper connections, it becomes natural to ask the next question, the one that sounds almost like science fiction and yet keeps turning up in serious physics. What if geometry itself is woven out of entanglement? There's a certain kind of question that only becomes possible after you've sat with entanglement for a while. At first, entanglement feels like a dramatic event. two particles doing something uncanny across distance. But if you keep watching, a quieter possibility begins to emerge. What if entanglement isn't something that happens inside space? What if it's one of the things that helps make space feel like space? This idea doesn't come from poetry alone. It comes from modern physics noticing a pattern. Whenever we try to describe gravity, horizons, and the deep structure of space-time, the mathematics keeps pointing back to entanglement, like a fingerprint showing up in places it shouldn't be, unless it belongs there. To ease into this, imagine a simple truth about information. If you cut a page out of a book and seal it in an envelope, you haven't destroyed the story. You've only hidden it. The story still exists and it still fits into the world. But if you take a book and shred it into confetti, something different happens. You may still have all the ink particles, but the relationships that carried meaning are gone. The story wasn't stored in the paper alone. It was stored in the structure. In a strange way, space-time might be similar. Not a thing built from bricks, but a thing built from relationships. And entanglement is the most precise language physics has ever found for relationship. One of the first places this became hard to ignore was in the holographic principle, a name that sounds like science fiction, but is really a careful observation about gravity. The holographic principle suggests that, in certain gravitational settings, the information content of a region of space can be described as if it lives on the boundary of that region, like a story written on the surface rather than stored in the volume. That sounds impossible at first. We're used to thinking that if you have a three-dimensional room, the room's reality should be inside the room. But gravity has a habit of breaking our intuitions, black holes especially. When you drop matter into a black hole, you're not merely moving mass from one place to another. You're changing the horizon, its area, its entropy. And the math suggests that the amount of information a black hole can hold scales with the area of that horizon, not the volume inside. That's the seed of the holographic idea. Gravity seems to compress the bookkeeping of reality onto surfaces. Now, the most famous concrete realization of this spirit is something called ADS, CFT, which is a kind of dictionary between two very different-looking theories. On one side, you have a gravitational theory, something like a universe with space-time that can bend and curve. On the other side, you have a quantum theory with no gravity living on the boundary of that space. And the shocking claim is, these two can be mathematically equivalent. Two descriptions, one reality. You don't have to remember the letters to feel the message. The message is that gravity and space-time might be an emergent language, an elegant way the universe summarizes deeper quantum information. So, where does entanglement come in? Here's the simple intuition. If the boundary theory contains all the information, then the pattern of how that boundary is entangled must encode the shape of the inside. Like a woven fabric, it's not the individual threads that make the cloth strong. It's how the threads cross, loop, and lock together. In the last decade, physicists found more and more hints that the geometry of space-time behaves like it's held together by entanglement. Almost like entanglement is the glue that keeps the universe from falling into disconnected pieces. There's an especially elegant image people use. Picture space-time not as a smooth, continuous sheet, but as something that could, in principle, be assembled from tiny building blocks of quantum information. If you entangle those blocks strongly in the right pattern, you get something that acts like a connected space. If you reduce the entanglement, the connectivity weakens. And if you remove entanglement entirely, the structure can pull apart into disconnected fragments, like a map that no longer has roads connecting the cities. This isn't just metaphor. In certain models, you can literally watch geometry change as entanglement changes. One of the most useful tools for making this idea visual is something called a tensor network. Think of a tensor network as a diagram that compresses a huge quantum state into a web of nodes and links, like a blueprint for how information is arranged and shared. Some tensor networks produce shapes that look eerily like curved space-times, not because someone drew a curved space by hand, but because the most efficient way to represent the entanglement naturally forms that structure. It's as if geometry is what entanglement looks like when you step back far enough. And then there is the phrase that grabbed the imagination of the internet, EREPR. ER refers to Einstein-Rosen bridges, what people casually call wormholes. EPR refers to Einstein-Podolsky-Rosen, the entanglement paradox that started this whole journey. The conjecture, spoken carefully because it's still an idea in development, is that certain kinds of entanglement might be equivalent, in a precise mathematical sense, to a kind of wormhole-like connection in space-time. Not the sci-fi version where you fly a spaceship through a tunnel and pop out near another galaxy. More like a geometric way of representing correlation. A bridge not for matter, but for relationship. In some calculations, when two systems are maximally entangled, the geometry connecting them resembles a smooth bridge in a gravitational description. And when the entanglement is reduced, that bridge pinches, thins, or breaks. So, entanglement begins to look less like a spooky message and more like a structural bond. This also helps explain why people get excited about the phrase space-time from entanglement, because it offers a possible route towards something physics desperately wants, a bridge between quantum mechanics and gravity. Quantum theory is naturally written in terms of states, information, and correlations. General relativity is naturally written in terms of geometry. If geometry can emerge from quantum correlations, then we are no longer trying to force two languages to merge. We're translating. Of course, this is not settled science in the sense of being a single completed theory. It's a direction, a set of clues that align in a surprising way. But the alignment is strong enough that it changes the emotional feel of entanglement. The spooky action begins to soften. Because if space itself is not fundamental, then it makes less sense to demand that all influences be local in the old way. Locality might be a rule that emerges when space-time is thick and stable, like the rules of traffic emerging once roads exist. Entanglement, then, isn't breaking the rules of space. It may be whispering that the rules of space are not the deepest rules. And this is where the idea becomes almost restful in a strange way. Because it replaces the image of an isolated universe with an image of a woven universe. Not a cosmos made of lonely points. A cosmos made of connections, quiet, structured, lawful connections, that sometimes show up in experiments as correlations we can't explain with classical stories. So, when you hear someone say, space-time might come from entanglement, you can translate it into something simple and honest. Maybe distance is not the first fact. Maybe relationship is. And if that's true, the next place this idea becomes more than beautiful is also the place where it becomes urgent. Because there is one kind of object in the universe that turns information, gravity, and horizons into a single unavoidable puzzle: black holes. Black holes are where entanglement stops feeling like a clever trick and starts feeling like a law the universe is quietly enforcing. Because a black hole is, in one sense, the simplest object you can imagine. From far away, it doesn't show you its details. It doesn't advertise what it swallowed. It only shows a few basic numbers: mass, spin, charge, like a sealed vault with no windows. And yet that vault is made from matter that once had an almost infinite amount of detail. The pattern of atoms, the chemical signatures, the history written into every particle's arrangement. So, the question arrives softly, but it does not leave. If a black hole eats a library, where did the stories go? In the 1970s, Stephen Hawking found something that made the question even sharper. Black holes aren't perfectly black. When you add quantum physics to the edge of a black hole, the horizon, you find that black holes should slowly leak energy. They should emit a faint thermal glow, what we now call Hawking radiation. At first, that sounds almost comforting. If the black hole radiates, maybe it can give the information back. But Hawking's original calculation had a chilling implication. The radiation looked thermal, random, featureless, like heat from a warm stone. And if the radiation is truly random, then it carries no detailed record of what fell in, which would mean the library is gone. Not hidden, not scrambled, gone. And that would be a deep problem, because quantum theory has a principle that it protects fiercely. Information isn't supposed to vanish. In ordinary quantum mechanics, time evolution is reversible at the level of the wave function. Lose information, and you break the rules that keep probabilities consistent. So, physics found itself trapped between two loyalties. Gravity seemed to say, the interior is sealed, the details are erased. Quantum mechanics seemed to say, the details can't be erased. Reality doesn't work that way. This tension became known as the black hole information paradox. Now here's where entanglement enters, not as decoration, but as the main character. Because Hawking radiation isn't just stuff leaving. It's born from quantum fields near the horizon, and those fields naturally produce pairs of correlated excitations. One partner escapes outward, the other effectively falls inward, when those pairs are entangled. In the simplest story, every time a particle escapes as Hawking radiation, it remains entangled with something behind the horizon. Over time, more and more of the outgoing radiation becomes entangled with the interior. If you think in terms of how much entanglement there is, you can picture an invisible thread count growing with every emitted particle. But there's a limit. A black hole has a finite entropy, often described as proportional to the area of its horizon. That entropy is like the black hole's maximum capacity for storing information. The vault is large, but not infinite. So, if the outgoing radiation keeps becoming entangled with the inside forever, you end up with a contradiction. The entanglement would keep growing past what the black hole should be able to support. And that contradiction is not a small technicality. It's a sign that our picture is incomplete. This is why people began drawing what's called the page curve, a simple graph representing what we expect should happen if information is ultimately preserved. Early on, as the black hole begins to evaporate, the radiation looks thermal and uninformative. The entanglement between the black hole and the radiation grows. But if information is not lost, then at some point, roughly when the black hole has radiated away about half its entropy, the behavior should change. The radiation should begin to carry more and more information, and the entanglement should begin to decrease. The curve rises, then turns, then falls. That turning point is sometimes called the page time. For a long time, that curve was more like a wish than a derived result. It was what you'd hope for if the universe kept its promises. And in recent years, something remarkable happened in theoretical physics. Using tools from quantum information and holography, physicists started getting calculations that reproduce a page curve-like behavior in certain controlled models. One of the key ideas involves what are called islands, regions that, in the mathematics, end up being included when you compute the entropy of the radiation. The language sounds gentle, but the implication is wild. It's as if the bookkeeping of what belongs to the radiation includes a piece that looks like it's inside the black hole. Not because information is traveling faster than light, but because the way space-time and entanglement are organized might not match our naive map of inside and outside. In these models, when you compute the entanglement carefully, you don't get endless growth. You get a turning point. You get the shape the page curve predicted. Again, not a final answer for every black hole in the real universe, but an evidence-shaped hint that the paradox may have a resolution consistent with quantum mechanics. And what kind of resolution would that be? One where the horizon is not simply a one-way eraser. One where information is not destroyed, but encoded, subtly, gradually, into correlations spread across the outgoing radiation. Not as a readable message, not as a clean confession. More like a watermark embedded across 1,000,000 pages, where any single page looks random, but the whole collection has structure. This is why black holes have become, in a strange way, laboratories for the deepest meaning of entanglement. Because the paradox is not just, where did the information go? It's also, what does it mean for information to be in a place at all? If space-time is emergent, if geometry is tied to entanglement, then black holes are where that relationship is tested under the harshest conditions. And if the hints are right, if the page curve is real, if the island story captures something true, then entanglement isn't merely a weird correlation between particles. It's a principle that may protect reality's memory. A quiet rule that refuses to let the universe forget. And that brings us to a softer question again, one that feels less like a paradox and more like curiosity. If entanglement can whisper through something as extreme as a black hole, where else might it whisper, more gently, in places that don't look cosmic at all? Sometimes, after we have followed entanglement to the edge of black holes and the scaffolding of space-time, it helps to let the mind drift back down toward places that feel ordinary. Because if entanglement is a real feature of nature, it shouldn't only appear in the clean, cold silence of a physics lab. In principle, it could leave faint fingerprints in warm, wet, complicated environments too, places where life is constantly buzzing with motion. This is where people start whispering about quantum biology, not as a claim that your cells are doing magic, not as a promise that life breaks the rules, more as a careful question. Are there a few rare biological tricks where quantum coherence or tunneling matters, even briefly, even locally? One of the gentlest examples comes from photosynthesis. In some light harvesting systems, energy seems to move through a network in a way that looks less like a single path and more like many possibilities explored at once, until the energy finds an efficient route. Researchers debate how quantum that really is in living conditions, but the broader idea is simple. Nature may sometimes take advantage of wave-like behavior for efficiency, if the timescales are short enough and the environment is just right. Another quiet candidate is enzyme tunneling. In certain reactions, tiny particles like electrons and sometimes even protons can slip through energy barriers they couldn't cross in a purely classical picture. It's not that biology escapes physics. It's that biology may, in a few corners, use physics as it actually is, probabilistic, wave-like, and occasionally surprising. And then, inevitably, the conversation wanders toward the most delicate frontier of all, consciousness. Some theories, most famously those involving microtubules, suggest that quantum effects might play a functional role in the mind. These ideas are controversial, heavily debated, and far from settled. The brain is warm and noisy, and most physicists suspect that fragile quantum states would decohere too quickly to matter at the level of thought. So, the honest stance here is the one we keep returning to on this channel: curiosity paired with caution. Quantum biology offers a humble kind of wonder, not the loud cinematic kind, the quiet kind, where life doesn't defy reality, but may, in a few subtle ways, lean into the same strange rules that bind stars, atoms, and black holes alike. And as we move toward our closing, we can hold that thought gently. Maybe the universe is stitched together by relationships, and sometimes those relationships leave their softest traces in the living world. When people first hear the word entanglement, it often lands like a ghost story. Two particles born together, sent far apart, measured in different places, and the answers still rhyme, as if they're sharing a secret across the dark. But tonight, we've been careful with the feeling. We didn't treat it like science fiction, or like a new kind of faster-than-light phone call. We treated it like what it is in modern physics, a tested pattern in the way quantum states can be shared. Not a message racing through space, but a relationship that was already there, waiting to be revealed. And once you accept that, gently, without forcing it, 3 layers begin to settle into place. The first layer is the simplest and maybe the strangest. It's real. Not as a rumor, not as a thought experiment. The universe has been asked the same question in many ways, and it keeps answering with the same quiet insistence. The correlations violate the limits that local hidden variable stories would demand. Over and over, in cleaner and cleaner tests, reality keeps choosing the quantum option. The second layer is practical. It's useful. Entanglement isn't only a philosophical headache. It becomes an engine. It becomes trust. It becomes a resource you can spend carefully to compute, to encrypt, to synchronize clocks, to sense tiny shifts in the world with a delicacy that classical light can't quite match. It's one of those rare ideas that moves from the page to the lab, and then from the lab into tools. And the third layer is the quietest one, the one that doesn't shout for attention. It changes the mood of reality. Because entanglement hints that the universe may not be built from isolated things the way our daily intuition suggests. It may be built from connections, from shared descriptions, from information that only becomes fully meaningful when you look at the whole. Not everything is entangled with everything else in any simple way. Decoherence is always there, washing out fragile quantum patterns in the warm noise of the everyday world. And yet, beneath that noise, the deeper grammar of physics still seems to be relational. It's almost as if the universe is less like a pile of separate objects, and more like a single vast story told in pieces. And if you're listening to this in bed, in the dim edge of the night, you don't have to solve that thought. You don't have to pin it down. You can just let it sit beside you, like a small lamp on a distant porch, present, steady, not asking anything from you. If you enjoyed this slow journey, I'd love to have you here again. You can gently tap, like, subscribe, or share where you're listening from tonight. Just a simple comment, even one word. It helps more sleepy minds find their way to these calm little corners of science. But for now, you've done enough. Let the room feel quiet again. Let your shoulders soften. Let your breathing take its own pace. And if you notice your mind still holding on to the idea of entanglement, you can picture it as thin, invisible threads, not pulling, not tugging, just connecting, quietly, patiently, across the cosmos. Nothing has to travel faster than light for the universe to be deeply connected, and you don't have to stay awake to understand it. Good night.